Hello, in this video I'd like to talk about how we can take the derivative of the function x to the x. This is such a fun function. If you see it show up, it probably will show up in combinatorics. If it's showing up in where x is some real number value as opposed to some whole number value, something has probably gone very wrong. But nonetheless, it's kind of a fun function to think about mathematically. So how can we take the derivative of this? Well, one option, which is wrong, is to apply the power rule, right? Remember, we subtract 1, we bring down the exponent, and we subtract 1 from the exponent. So this is one wrong way of computing the derivative of this original function, and I've seen this tons of times in calculus classes before. But if you've just done taking the derivative of various exponential functions, you're probably also thinking about another rule. Here, if we want to take the derivative of some constant to the power of x, that derivative is going to be, let's see, it's going to be a to the x times ln of a. So if you've just done derivatives of exponential functions, perhaps this is fresh in your mind, and so you think, oh, well, let's try using this rule to calculate the derivative of this function. And so the answer that you get is going to be x to the x, right? In this case, a is x, times ln of x. And of course, that's also wrong, because this rule, just like the power rule only works when the exponent is a constant, and this rule here only works when the base is a constant. But here's the fun part. If you take these two wrong answers and add them together, you get the correct answer. This is, in fact, the derivative of this original function here. And this isn't a coincidence in the slightest. This is actually something really interesting is going on here. So let's look into what that is. But first, we need to talk about what it means to take the derivative of a multivariable function. Suppose that we have some sort of function, f, that takes in elements of Rn and outputs elements of Rm. That is to say that the input to the function are n-dimensional vectors of real numbers, and the output are m-dimensional vectors of real numbers. Then the derivative, which I'm just going to use traditional derivative notation. Sometimes you'll see this called the Jacobian matrix, but it's really the derivative, and it behaves exactly like the derivative in all appropriate ways. The derivative of this function is going to be an m by n matrix. And in particular, this derivative is going to be equal to this matrix of partial derivatives here. And in particular, the utility of the derivative, right, is it's the multiplication factor when we construct a linear approximation, right? If we have some sort of function, f of x is going to be approximately equal to f prime of a x minus a plus f of a. And in the multivariable case, x is going to be an n-dimensional vector, f of x is going to be an m-dimensional vector, and so x minus a, this here, is an n-dimensional vector, and then we multiply that by an m by n matrix, and we get an m-dimensional vector, and we add that to this, which is also an m-dimensional vector, to get an m-dimensional vector, which is going to be an approximation for f of x, provided that x is close to a. And this approximation works in the multivariable case, right? You can imagine making a small change to the input of the function. That small change is going to be a vector. Maybe we're changing multiple inputs at once. Maybe we're just changing one input, in which case it'll be a bunch of zeros and then the change to that one input and then a bunch more zeros. And we take that change and we multiply it by this derivative matrix here. And that's going to give us the change, right? This here, we started off at f of a, and then this is the change in the input. We take that change in the input, we multiply it by the derivative, and that's going to give us the change in the output, the amount that we need to add to f of a in order to get f of x. So it really does make sense, and you can test this out. You can test this out on various unit vectors and kind of see what happens, and you can see that it really makes sense that this should be the derivative of f in this case. So now let's go back to our original problem, taking the derivative of x to the x. And in order to do that, I'm going to write x to the x as a composition f of g of x, where f is going to take in a two-dimensional vector, xy, and return x to the power of y. And g, well, in order to get this to make sense, g of x is going to have to be the vector xx. And if we want to, we can take a look at the typing information. We have that f is going to be a function from R2 to R1. I'm going to think about these as one-dimensional vectors instead of scalars. You can think about them either way. And then g, I'm going to think about as a function from R1 to R2. And so these compose, and we know what dimensions their derivatives are going to have. F is going to be a 1 by 2 matrix, and G is going to be a 2 by 1 matrix. So let's think about this. What does the chain rule say, right? The chain rule says that the derivative of this, is going to be equal to f prime of g of x times g prime of x. And in this case, this is going to be matrix multiplication. The chain rule works perfectly fine in the multivariable case as long as you replace this multiplication here by matrix multiplication. This is the correct order of multiplication for these things. Note that when you're multiplying matrices, the order that you multiply matrices in matters. But you do a little bit of dimensional analysis and you figure out that this is in fact the correct order to write the chain rule in. So what is f prime? F prime is going to be a 1 by 2 matrix, and in particular it needs to be the sort of thing that we could multiply by a two-dimensional vector in order to get a scalar, just like how applying f to a two-dimensional vector gives us a scalar. And so what we can expect really is essentially a dual vector here, where we're using kind of a column vector standard notation. So here, the derivative is going to be partial f, partial x, and partial f, partial y. And we'll calculate those in just a moment. And of course, we need to evaluate this derivative not just where it stands. In this case, that actually doesn't even make sense in terms of dimensional analysis. We need to evaluate this at g of x. In particular, when xy, when the input to this thing is equal to xx. So this here is our derivative of f evaluated at g of x. And then we take this and we multiply it by g prime of x. And that derivative, so g of x is the sort of thing that takes in a scalar and outputs a two-dimensional vector. And so g prime of x needs to be the sort of thing that we could multiply by a scalar and get a two-dimensional vector. So in particular, it's just going to be a two-dimensional vector. And that vector is going to be partial g1 partial x and partial g2 partial x, right? The first output, the derivative of that with respect to x, and then the second output, the derivative of that with respect to x. So let's actually evaluate these things. Partial f partial x, that's going to be the derivative of x to the power of y, treating y as a constant. Well, now we can actually use the power rule because we're treating y as a constant. So this is actually going to be y times x to the y minus 1. Partial f partial y, again we have to use this other power rule, the rule for taking derivative of exponential functions. So we're taking the derivative of this, treating x as a constant, taking the partial derivative with respect to y. That's going to give us, according to this rule, x to the y times ln of x. So this here is our matrix f prime, and actually we need to evaluate this when xy is actually equal to xx. And so what that means is that all of these y's become x's because we're evaluating it at g of x. And then we need to multiply, well, the partial derivative of the first output of g with respect to x is just 1, and the partial derivative of the second output of g with respect to x is just 1. And so we're multiplying this matrix by this matrix here. And of course, well, what does it mean to multiply two matrices together? Well, we take these elements. So this is a 1 by 2 matrix times a 2 by 1 matrix. And so the result is going to be a 1 by 1 matrix, which that's just the scalar. And the entry in that matrix is going to be the product of these two plus the product of these two. And so what that means is that this result here is just going to be this times 1 plus this times 1. In other words, this plus this. So hopefully you can take away the fact that the derivative of x to the x is this particular formula here, right? We take the derivative wrong one way, and we take the derivative wrong another way, and we add the results together. This is not a coincidence at all. This is a simple consequence of the multivariable chain rule. And there's lots of useful facts that you can take away from this. The first is that there's nothing special about the x to the x function. Anytime you have any sort of formula whatsoever that has a bunch of x's in it, the total change to that formula is simply the sum of the changes induced by each individual x. So you simply take the derivative, treating one x as a variable and all the other x's as constants, and then simply do that for all of the x's and then add up the results. So let me show you this in action with a more complicated example. Suppose instead we wanted to take the derivative with respect to x of, let's say, x plus 2 squared times x times x times 5 to the x. So it's very rare for anybody to memorize the triple product rule. You have to think about it a little bit to remember how it works. But using this trick, we can work out this the derivative of this triple product immediately. We treat this x as a variable and these as constants. And so the derivative of this is just a constant times x plus 2 squared. So the derivative is just going to be the derivative of x plus 2 squared times that constant. If we treat this x as a constant and as a variable and these x's as constants, then it's just going to be some constant times x. So it's just going to be that constant. And then finally, if we treat this x as the variable and these x's as constants, well, it's just going to be this constant here times the derivative of 5 to the x. And so here we were able to recover the triple product rule without having to memorize anything. So that's actually kind of nice if you want to like avoid having to like associate things or actually have to memorize the triple product rule. So I hope this was enlightening, and I will see you in a future video.